Hi, so welcome back to chapter 8.1 where I introduce you to Keras and TensorFlow. So what exactly is Keras? I've mentioned it countless times on this course, but I haven't actually told you precisely what it is. So Keras is a high-level neural network API for Python, and it makes constructing neural networks, all types, not just CNNs, but all types of neural networks. It makes it extremely easy and extremely modular. Just to add layers, swap in stuff, change different things, configure your loss functions, configure your different types of activation functions. It's quite nice. It has the ability to use TensorFlow, CNTK, which is used for natural language processing, and Theano, which I used to use quite a bit of Theano. However, I've now moved to TensorFlow and I haven't looked back. Not because Theano is bad. Theano just basically has stopped being updated now. Project is pretty much done and closed, and everyone is pretty much adopting TensorFlow now. And it was developed by Francois Cholet, and this has been a tremendous success in making deep learning much more accessible to the masses. So what is TensorFlow though? I said Keras used a TensorFlow backend, but what exactly is a backend? Okay, so TensorFlow is an open source library that was created by the Google Brain team in 2015. Probably was being used inside of Google internally for many years prior to 2015. And basically it's an extremely powerful, extremely efficient and fast machine learning framework that is used for high performance numerical computation across a variety of platforms such as CPUs, GPUs, and TPUs. These guys at Google Brain, they developed this basically super fast library similar to NumPy, but basically incorporated it and built it around deep learning. So they have all these deep learning functions that are part of the TensorFlow framework. It too actually has a Python API, and it pretty much is accessible and easy to use, but Keras is much easier to use. So why use Keras instead of pure TensorFlow? As I said, Keras is extremely easy to use as it follows basically a Pythonic style of coding, and it is extremely modular. You don't even have to be a proficient programmer to use Keras. This modularity means that we can actually just start doing different things with our neural nets or CNNs. We can easily change cost functions, optimizers, initialization schemes, activation functions, try different regularization schemes, introduce more layers, reduce number of filters. All of those things are done super easily inside of Keras. So it allows us to build these powerful neural nets quickly and efficiently. And obviously it works in Python. And Python is one of my favorite, actually it is my favorite programming language ever, because it makes so many complicated things super easy. TensorFlow is definitely not as user-friendly and modular as Keras. I've used TensorFlow a bit, to be fair, but I was using Theano at that point, and Theano actually was quite hard, so TensorFlow seemed easy for me at that point. However, nothing beats Keras in terms of ease of use. So unless you're doing complicated models or academic research, or basically working for some sort of high performance startup, you don't necessarily need to use pure TensorFlow for anything. So now you're ready to see some actual Keras code. Well, it's actually Python code, but we're using the Keras library. And this is how we actually construct and build models inside of Python. So firstly, we import the sequential model from Keras. Basically, the sequential model is the main type of model you'll be building in Keras. Basically, all the CNNs and neural nets I've shown you before were sequential models. If you're doing something exotic, then it will probably not be sequential, but that is rare and probably beyond the scope of this course right now. It's basically academic research. So let's move on. So we defined our model here. We initialize it by running this line here, sequential, these two brackets. And then now let's add some convolutional layers to it. So before we do that, we have to import these layers from Keras here. So from keras.layers, we import dense, dropout, flatten, conv2d, max pooling. Now I don't have dropout here, but it's being used in the model we actually are going to code. So I left it in just so you guys know how it's referred to here. Okay. So firstly, model.add. We're adding our first layer here. So our first layer is a conv2d. That's what we call it. And now we have open brackets here, and we have some parameters to fill out. So let's go through these parameters. First one is a number 32. then the kernel size we can see here, then the type of activation we use, and input shape being equal to input shape. That's a bit confusing. I'll explain that to you shortly. So let's go through each one. First one here, 32, that specifying firstly the number of kernels or filters. So in our first layer, we're using 32 filters of kernel size 3 by 3 with an activation function using ReLU, and our input shape is equal to input shape, and that's because previously above this code we created an input shape parameter, or variable I should say, that was 28 by 28 by 1. That's our input shape we use. So I just left it out here for convenience because we tend to leave it out and just have it defined outside of this scope of this declaration here. Now to add another layer, it's as simple as model.add. Keras is so easy to use. You just keep using model.add, and it stacks these layers on top of each other, starting with the first to the bottom layers. So now we add another convolutional layer, 64 filters this time, same kernel size, and note we don't need to specify kernel size every time we do it. It knows that the second parameter is kernel size, so it's 3 by 3, and again, activation, ReLU. And now, you've noticed, we don't need to specify an input shape here. And do you know why? That's because this layer is directly connected to this layer. So it takes the output of this layer, and it knows the output, so the output of this layer is effectively the input into this layer. So we no longer have to declare inputs anymore. So now you can add a max pooling, and I said before we're going to use a max pooling of 2 by 2. So that's simple here. We have model.add, max pooling 2D, and specify the pool size. Open brackets 2 by 2, close brackets for this here, close brackets for this here. And then we do a flatten. I haven't discussed flatten. Flatten is an actual layer. It's basically a function we do that we use to feed the dense layer or the fully connected layer. You'll see it visually in the next diagram on the following slide. Basically, we then add a dense layer here with 128 units, all being activated by ReLU. And this is connected to another dense layer here, which outputs the number of classes. So classes in this dataset here were 10, because we're using the MNIST dataset, 0 to 9. And we use the softmax activation to get basically the probabilities. So I hope you think this is quite simple, because to me this is quite basic. You may take a little while just to get familiar with how these things work, but you'll get used to it in this course, I guarantee it. So let's take a look at what we've built here. Okay, so this is actually what we have built so far. So we have our input image here, 28 by 28 by 1, 1 because it's grayscale. If it was a color image, or RGB image, it would be 3 depth here. So as you saw before, we have 32 filters here, connected to another conv layer with 64 filters here. And you may have noticed the size of the image shrank here. It became 26 by 26 and then 24 by 24. And that's because we didn't use any zero padding. And I'll show you guys later on in code how to do zero padding. It's quite simple. But for now, just remember, when you don't use zero padding, our input image, our convolutional feature map size reduces from the input image size. So we have these two conv layers stacked here. Then we have our max pooling, which basically shrinks this by half. I have a dropout thing here, but we didn't actually use dropout before in the code. But in the actual code, when we start our project, I'll show you quickly how to actually implement dropout. It's one line, super easy. What I wanted to show you though was we have the flattened layer here. Now the flattened layer, if you go back to it here, was just flattened in brackets. And what does that actually do? Flatten basically takes this multi-dimensional matrix, 64 by 12 by 12, and basically turns it into a row of 9,216 columns. So what this means here is that we just flattened this matrix. So instead of having 12 by 12 by 64, imagine you just built an entire long row where it's the first 12 here, then second 12, and then it's just consecutive long, basically a long row. And that becomes this output box here. And now this output box here is fed into the fully connected layer here with 128 nodes. Let's go back to it here. So we defined it here, and each node is connected to a ReLU activation unit. And then finally, we connect this to our final dense layer with a softmax activation function, and it outputs to 10 nodes. 10 nodes because our MNIST dataset has 10 classes. So that's how we get our probabilities here. So it's not illustrated here, but later on you will see it. So now that we've built our model, we are ready to compile this model. So compiling simply creates an object that stores our model we've just created. And we can specify our loss algorithm, our optimizer, define our performance metric that we want to look at. And additionally, we can specify parameters for the optimizer, such as learning rates and momentum. So this is a simple modeler compile code here. We have our categorical cross entropy defined as a loss type. We have our optimizer, SGD, being stochastic gradient descent, and we have our metrics to look at, being defined as accuracy. So how do we fit or train our model now? So following a simple, basically what sklearn, which is the most established and popular machine learning library on Python prior to TensorFlow and Keras, basically they just applied model.fit, where they use the training data, the training labels, xtrain and ytrain. That's what they are. You'll see them referred to in the code soon. Specify a number of epochs and the batch size. Now the batch size, this doesn't impact your learning that much significantly. However, you basically should use a largest batch size as possible that your memory allows. So you can experiment and try it. You will note, if you try a too large a batch size, your kernel will crash. So generally I tend to not avoid having my kernel IPython notebook crash. So I'll use basically a batch size of 32 for pretty much small images or 16 for larger images. And once we do that, we can now evaluate and generate predictions afterward. So by running model.evaluate and feeding it the xtest and ytest labels with a batch size, we can get these metrics here, this metrics parameter, this metrics object. And then we can use that to actually look at different graphs and different interesting performance information from our model. And if we wanted to predict an individual point, like you have an image and you want to get the actual class it belongs to, you can use model.predict. Model.predict allows us to feed one image at a time, or you can feed the entire data set here as well. So that's it. So now let's get started to build our own MNIST handwritten digit classifier.